Sort of a variety.
Okay.
I have a unit study guide.
Okay.
So,
you're going to verbalize it?
yes.
Okay.
So the first one is find rectangular coordinates.
Okay.
3, comma, 7 pi over 6.
Those are the polar. Whoops. To find the rectangular, we need these conversion factors. What is x equal to?
R times cosine of theta.
And what's y?
R times sine of theta.
So that's what we're going to do. Those two. In other words, to find the x coordinate, what's r?
3.
And what is the cosine of 7 pi over 6?
Negative 3 pi over 2.
Put the minus sign in front of the 3, but it's root 3 over 2. So there's the x coordinate. Y coordinate is 3. What's the sine of 7 pi over 6?
Negative 1/2.
There's the y coordinate. Easiest way to go is from polar to rectilinear. You only have to use these two conversion factors.
Right.
A lot harder to go the other way. Then you have to solve for theta, and that involves a more complicated procedure. Okay, what else you got?
Well, find the polar coordinates.
Okay.
Of 4, comma, negative 4 root 3.
So the first thing we solve for is theta. Or we could solve for r. R squared is, in other words, there is a pretty important conversion factor that we have to use on these. So we're going to solve for r that way.
Right.
Go ahead and do that. What do you get? What's the square root of, so it's the square root of 16 plus 16 times 3, 48, square root of 64, 8. Okay? Now, theta is the tricky part. We've solved for r. Theta. And this is how it's actually defined, and it's kind of weird. It's not weird, it's just if x is greater than 0, that's what theta is. Inverse tan of y over x. If x is less than 0, notice I'm not talking about y over x, I'm talking about x only, then theta is equal to the inverse tan of y over x plus pi.
Right.
There's your two equations for solving for theta. And you'll want to remember those because the stuff you're going to get to next in math, you're going to have to solve for theta quite a bit. And so this adding pi when x is negative. And notice that it's not the argument that has to be negative, it's just the denominator.
Right.
Now, so in our case, x is positive, so we're going to use the inverse tan of root 3, negative root 3, right? In other words, we're going to take the inverse tan of minus 4 root 3 over 4. So that's the inverse tan of negative root 3. What angle is that?
Negative pi over 4.
I don't think so. I think that's a 3060.
Okay.
In other words, if I draw my 3060 triangle, the dimensions are 1, root 3, and 2. So whenever you're dealing with a root 3, you're generally dealing with a 30-60 degree angle, one or the other. The 45 degree angles involve 1 over root 2. So when you see a root 3 in an argument, we're probably looking for a 60 degree angle. And it's minus 60. In other words, if you put that into your calculator, what is the inverse tan of minus root 3? It'll give you a negative angle. It'll give you minus 60 degrees. So I suppose there's two choices here. One is to go ahead and go with the negative angle, but the other would be to go ahead and make that a positive angle. It's positive 300, right?
Right.
Now, I don't know which one your teacher prefers, or for that matter, what the book would. I don't think there's any problem with negative angles in polar coordinates. Here, let me look at some, see if I've got some polar coordinates and see if any of them have a negative angles. You know, I don't see any. Oh, yes, I do. I'm looking in my book. Yeah, you can have negative angles with polar coordinates.
Okay.
So I'd be tempted to go with the first one because it's one less step. And if you're getting this out of your calculator, then it's always going to give you that negative angle. It's never going to give you the 300 degree angle as an answer.
Right.
So let me ask this. What's the inverse tan of 1 divided by 0?
Pi over 2.
Good. Now, where else in math have you ever seen where it's okay to divide by 0? Nowhere.
Yeah.
And in fact, if you enter that into your calculator, it'll cough on you. If you enter inverse tan of 1 divided by 0, it will not give you 90 degrees like it should. It doesn't like division by 0. But this is one of the few places where it's appropriate, is because that's when the angle is pi over 2, the tan of pi over 2 is infinity, which is what 1 over 0 basically is infinity. It's just a question of whether it's pi over 2 or minus pi over 2. If it's inverse tan of minus 1 divided by 0, then the answer is minus pi over 2.
Right.
Okay. What else?
This next one says write in polar form.
Okay.
It's negative 2 minus 2 root 3 times I. And the I don't think it's inside the square root.
No, it isn't. And I believe what you mean is minus 2 root 3i. That is a complex number in standard format. This is the standard format for a complex number. So in your case, a is minus 2 and b is minus 2 root 3. With me?
Yeah.
Okay. So in polar, the trigonometric polar form is R. I have to look this up. I might. You have it written anywhere?
I don't know. Sorry.
Sorry. I don't want to give you something that isn't correct. Okay, I got It's r times the cosine of theta plus I sine of theta. That is the trigonometric polar form of a complex number. In other words, all complex numbers, which is what you gave me, can be written in this method. Okay?
Right.
Now, theta, again, is basically A divided by B, or it's the inverse tan of, instead of y divided by x, it's b divided by a.
Right.
So in our case, it is the inverse tan, and the same rule applies. If a is a negative number, you have to add pi. So it's going to be the inverse tan of minus 2 root 3 divided by minus 2, which is the inverse tan of root 3 plus pi, because the denominator is negative. Only because a is negative. Doesn't have anything to do with b. With me?
Yeah, okay.
Okay. So inverse tan of root 3 is 60 degrees. We just did the inverse tan of negative root 3, which was negative 60, so this is 60. Plus 180, the angle that they're referring to is 240 degrees. What quadrant's that in?
Third quadrant.
Correct. And should it be? Yeah, if I look at this complex number and I treat the minus 2 as the, in other words, when you plot complex numbers, the real part goes on the horizontal, the imaginary part goes on the vertical. So if I'm graphing that, I'm going 2 units to the left, and then I'm going down to root 3. So there's the point on the complex graph. And this is the angle. In other words, if I draw a ray, that is a 240 degree angle. And it makes sense. That's why we had to add pi, because otherwise I would have gotten 60 degrees and I'd have been in the wrong quadrant.
Okay.
So that's why you add pi when the denominator is negative. So now, what's r? How do I figure out r? Think of it as the Pythagorean theorem.
Right.
In other words, it's going to be the square root of a squared plus b squared. That's what r is. So in this case, it's the square root of 4 plus 12, 16, so r is 4. So now the trigonometric representation of that complex number is 4.
Isn't b negative 2 root 3?
Yes. I squared that and got 12.
Okay, gotcha.
Okay. So the final answer, and this is almost surprising, because this is the final answer. In other words, it's surprising in the sense that we're not simplifying it. And we're not supposed to.
Right.
In other words, if we simplified it, in other words, if I went ahead and figured out what cosine of 240 is and sine of 240 and distributed, guess what I would get?
Negative 2 minus 2
Yeah.
root 3, yeah.
Exactly. And that's why you don't simplify it, is because you always go back to that. But that's one way you could prove that this is equal to that, is by doing the math. and the math is the cosine of 240 is negative 1/2. The sine of 240 is negative root 3 over 2. Distribute the 4, you get minus 2 minus 2 root 3 I. In other words, you get what we started with.
Right.
So that proves that those two are the same. But that's the answer. You don't simplify it. Simplifying it puts it back in the same form that you started with. That's why you don't simplify. But it is one way to check your work. In other words, by going ahead and simplifying this, making sure you come up with what you started with.
Okay.
Okay? Okay? What else?
It says use DeMauve's theorem to compute
Go ahead.
negative 4 root 3 plus 4i all raised to the 5th.
Okay. That's the beauty of DeMauve's theorem. I don't know how to pronounce it either. That's a hard one. I'd hate to have to do this manually, right? So, DeMauve's theorem says that if I convert this to a trigonometric form, I can easily solve it. And the equation is, hold on, here's the general equation. Z to the nth equals R to the nth times cosine of n theta plus I sine of n theta also. In other words, this trigonometric, the z is the complex number in the parentheses. So if I want to raise that to the 5th power, first of all, let's figure out what r is. That must be 12 plus 16 square root of 28. 2 root 7.
Yeah.
Is that what you got? In other words, r is the square root of a squared plus b squared. So it's the square root. That's 12 when I 16, excuse me. 16 times 3 is 48 plus 16. That's better, that's 64. I was going to be disappointed with them in giving us these fractional numbers. So r is 8, not 2 root 7. So if I want to know what this is, then it's 8 to the 5th power, that's what n is, times the cosine of 5 times theta, which we haven't figured out yet, but we will here in a second, plus I sine of 5 times theta. Let's figure out theta. What's theta?
Inverse tangent, right.
Of
4 over negative 4 root 3 plus pi.
Plus pi, there you go. And that is a negative 30-degree angle. In other words, you still have to use the signs. In other words, 4 divided by negative root 3 is negative root 3. Negative 1 over root 3, excuse me. which is 30 degrees, plus pi gives us an angle of 150 degrees. That's second quadrant. If you look at these two complex, or if you look at this complex number, the A is to the left of the imaginary axis. The B is positive, that's second quadrant. So we're in the right quadrant with our angle. And that's always worth kind of keeping an eye on, because it's pretty easy to make a mistake with this complicated formula for theta. So once you come up with the angle that you think is correct, now you can check it to make sure it's in the right quadrant. It is. So here's my answer. 8 to the 5th times cosine of 750 degrees plus I sine of 750 degrees. And isn't that a whole lot easier than taking that to the 5th power?
Yeah.
So de Moivre this is a brilliant theorem. This part right here is a nice and handy way of doing binomial expansions. In other words, I could use the binomial expansion theorem here, but that would be terrifically hard. That's going to be a whole lot harder than using de Moivre's theorem.
Right.
And whatever these come out to be, cosine of 30 is root 3 over 2. Sine of 30 is 1/2. And so you'll come out with a number. In fact, let's carry this forth. Let's not drop it there. Do you have a calculator? What's 8 to the 5th power?
32,768.
So I'm going to multiply that by the cosine of 30 plus sine of 30. So whatever that distributes out is your answer. That is what that number to the 5th power is. Okay? Now, this is like a little magic trick. In other words, it's a quick way to take numbers to big powers. I guess you could do that in your calculator also. You can enter a complex number in your calculator, can't you?
Yeah.
And then take it to a power. So, in other words, so far, not that impressive. But when you start finding roots of numbers, like, what are the 8 roots of the number 1? Well, who the heck knew there were 8 roots, first of all? But there are. In other words, what I'm going to find are 8 numbers that when multiplied together by one another, I'm going to find 8 different numbers that when you square it, you get 1. We know 2 of them, right? There's 1. There's 1 root of 1. There's another root of 1. Minus 1 times minus 1 is 1. Well, I believe that this is another one. Not sure. I'd have to do it. But there's all kinds of combinations of complex numbers that when multiplied by themselves equal 1. So there actually are 8 roots of 1. And in fact, if my memory serves me, there's as many roots as you want. And you can find them all with de Moivre's theorem. Okay, and you may have problems like that to do, you may not. I've got one in my book that's like that, but they may not take it that far for you. That's a pretty tough concept, actually, knowing that there are 8 roots of a number. In fact, there are 16 roots, there's 20 roots, there's 100 roots of the number 1. And I could find them all with de Moivre's theorem. Now, one other interesting piece of fact is one of the most famous equations, in fact, without a doubt, the most famous equation in all of math is the following. You familiar with this?
I think so.
It's called Eulers equation. And what's amazing about it is that it relates the 5 most important numbers in all of math in this equation. It's a little bit like Einstein's E equals mc squared. I mean, how beautiful does it get? How must Einstein have felt when he worked out all the complex math and he came up with E equals mc squared? Wow, that must have just blown him away. Well, same thing with Euler's equation. Leonhard Euler. And if you think about this, this is an amazing equation. And you know how he got it? By using the trigonometric polar form of a complex number. I watched a professor at MIT give a session that was on YouTube. He'd filmed it. And it was all about using the polar trig representation of a complex number to calculate this equation. That's how you do it. That's how you come up with this equation. But this is an amazing equation because E is 2.71, has nothing to do with circles. Pi has everything to do with circles. And then we got this imaginary number here. How could E to the I pi equal -1? But it does. Quite amazingly. So anyway, that's my little bit of math history. What else you got tonight, Wade? That's the motivation for why you learn the Morse theorem. And it is very useful in higher mathematics.
Okay, so this next one is a vectors problem.
I didn't quite hear that. What?
It's a vectors problem.
Practice problem?
Vectors.
Vectors. Okay, go ahead.
A plane is flying at 600 kilometers per hour, bearing 30 degrees south of east. A tailwind in the direction of 45 degrees south of east has a velocity of 40 kilometers per hour.
What's the net direction and speed of the plane?
Yeah, that's one part. It's asking me to list the different things that lead up to that.
Okay, let's go through each step. What's the first thing it's asking?
Find the velocity vector of the plane.
Okay. "30 degrees south of east." It's not the way bearings are usually given, you know. Bearings are usually given east of north. But that's okay, as long as we can figure it out. That's what they're talking about, I believe. Right? Isn't that south of east? Okay. And it's a vector, so it's got magnitude of 600 km per hour in that direction. They want the vector equation. They want you to break it up into its components, is what I'm guessing.
Okay.
In other words, the way I'm going to solve this problem is I'm going to break the plane up into its east and south components. I'm going to do the same thing with the tailwind. And then I'm going to add the east and south components together, come up with a resultant. In other words, where's the plane actually going to go with the tailwind? It might be headed 30 degrees south of east, but it ain't going to end up going that direction. So let's break this up. And what's useful to know here is that it's easy to figure out the horizontal and the vertical components of this vector. The horizontal components are the cosine of 30 degrees times 600.
Right.
So that's square root of 3 over 2. So that's 300 root 3. That's how fast it's going in an easterly direction.
Right, that's the x.
Right. In other words, when I'm breaking it up into its components, I'm breaking it up into its horizontal and its vertical. So that's its horizontal component, and it's in an easterly direction because it's positive. Now, the vertical component is 600 times the sine of 30 degrees, which is just equal to 300. So this plane is the equivalent if I had two separate vectors. One was this and the other was this, and you added them together, you would get our plane, our planes vector.
Right.
You with me?
Yeah.
Now, do the same thing with the wind. Don't need this anymore, or that. So, let's look at the tailwind. It's 45 degrees south of east, and its vector magnitude is 40. So let's figure out what its horizontal component is. Let's label these. That's the horizontal, that's the vertical. Or the x component and the y component. And notice the y component is negative. By negative, I mean it's going on the vertical axis. Negative is down, positive is up. On the horizontal axis, positive is to the right, the east. Negative is to the left, the west.
Right.
And I can do that by either calling this a negative 30 degrees, and that's the way I get my negative sign on the 300. But I don't want to do that because the magnitude of the vector is always a positive number. It's not really negative 300. It's 300 in a southerly direction is what it is.
Right.
Okay. So let's figure out our wind. What is the horizontal component of the wind? Remember, it's the magnitude of the vector times the cosine of that reference angle.
It's negative or positive 20 over root 2.
I think it's 20 root 2.
20 root 2.
No, you're right. Let's see. Cosine of 30 is root 3 over root 2 times 40. Yeah, it's 20. It's just 20 root 3.
20. Oh, okay. Right.
Okay.
Cosine.
And the...
It's 45 degrees though.
Right. So I know that it's the same vertical component. In other words, that's the same as if we had two winds. Instead of one wind blowing at 45 degrees south of east, let's say we had a horizontal wind and a vertical wind that were this magnitude. That would be the same exact effect on the plane.
How did you get 20 root 3?
Yeah, maybe I did it wrong. I got 40 times the sine of 45 degrees, which is root 2 over 2. I did it wrong. It's 20 root 2. Right?
Yeah.
Okay. My apologies.
Oh, that's okay.
No, I'm glad you picked it up, actually. That shows you're paying attention and following my math. Okay, now we're going to add the x component of the wind to the horizontal component of the plane. So the new horizontal component of the wind and the plane combined is 20 root 2 plus 300 root 3. With me?
Yeah. Should I calculate that?
Not yet, not necessarily. Maybe. We'll see here. Let's first of all figure out what it is, and then we can figure out how to get these numbers. What's the vertical component of the plane going to be?
Negative 20 root 2.
Well, it's still 20 root 2 plus, they're both in the same direction. In other words, they're both in a southerly direction, right? This wind is helping the plane in a vertical direction or in a southerly direction and an easterly direction. So the way I deal with this is that's its speed going to the east. This is its speed going south. In other words, I don't use the negative signs because once again, magnitude is always positive. The magnitude of a vector is positive, always, because it's the square root of two numbers squared, so you're dealing with nothing but positive numbers. So the only thing that negative and positive has to do is tells you which direction. In other words, if that wind was going the other direction, well, both its horizontal and vertical components would be subtracted from the airplane, not added to them. It depends on whether it's helping or hurting.
Okay.
This case, the plane's horizontal was positive to the east, so it added to the plane, to the wind, and the wind's vertical was to the south, same as the plane, so that's added to the plane. And these are, you could give those as the answers. Those are exact answers. However, the next question is, what direction does the plane fly and with what speed, right?
Right.
Okay. Well, now we got to go back the other way. In other words, if I draw a picture and my plane is going 20 root 2 plus 300 root 3 in that direction, and it's going 20 root 2 plus 300 in the southerly direction, how do I figure out the true angle that it's going?
You add them together.
Well, you could use the Pythagorean theorem.
Oh, right.
It's a right triangle always, whenever you complete that triangle. So I need this angle. So that angle is the inverse tan of the vertical over the horizontal. See why? In other words, this side right here is also 20 root 2 plus 300. And so the horizontal is 20 root 2 plus 300 root 3. The vertical is 20 root 2 plus 300. You could certainly solve for the magnitude by doing the Pythagorean theorem, and that will solve for the magnitude. But if I want to solve for theta, I'm going to do the inverse tan of this measurement divided by that measurement.
Right.
So go ahead and do that. We'll check because we know this should be a reference angle greater than 30 degrees. Because the plane was headed at 30, but the wind was at 45, so it's going to push it a little further south at a southerly angle. So let's come up with that angle. What's the inverse tan of that numerator? Excuse me. I got it backwards. The inverse tan of the y coordinate divided by the x coordinate.
I got 30.9 degrees.
Okay? That's what that angle is. 30.9 degrees. So the plane is actually going to end up going at a bearing of 30.9 degrees and at a speed that is the square root of the sum of the squares here. And I don't know how else to get that, but no, I guess you could use trig functions. In other words, once I've solved for that angle, now you could say the sine of 30.9 is this number over x. So there's various ways to solve for the magnitude of the plane. The other thing we know is it's going to be greater than 600 miles an hour.
Right.
Because the wind is helping in both directions. So you want to come up with that just to make sure, and you can do it either way. You can use the Pythagorean theorem, or you can use the sine function, or the cosine function to figure out that hypotenuse length.
Okay. Right.
Probably a little harder to do using the Pythagorean theorem because the numbers are so bizarre.
Yeah, it's a little jumbled.
Whereas the sine, that's probably easy to do. In other words, take the sine of 30.9 and it's equal to 20 root 2 plus 300 over x, and solve for x.
Right. Alright, I got 638.7.
And that's why planes take longer to go to Florida than they do to fly back from Florida to Colorado. Usually by about an hour. That's because there's the standard wind stream. I believe it's west to east. Yeah, all the weather goes west to east. So the standard wind stream is west to east.
Right.
So when you fly to Florida or New York, you got a tailwind. When you fly back, you're flying into a headwind. Yeah. But this is a great problem because it really illustrates the essence of vectors and how you handle multiple vectors. In other words, we have a vector for the plane and we have a vector for the wind, and we have to meld them together. But there's all kinds of problems like that. You could have a soccer ball where you got 3 people tugging on it. Okay, you got somebody tugging on it in that direction, you got somebody tugging on it in that direction at 50 pounds of force. This person's stronger, he's pulling out 75 pounds of force. And the question is what pounds of force have to be in that direction so that the ball does not move? And the way you solve it is you break that up into its x and y components. You break, excuse me, I'm pointing with my cursor. You break that up into its x and y components. You break that up into its x and y components. Add them together and know that all x components have to equal 0 because the ball's not moving. And all y components have to equal 0 because the ball's not moving. If you had a net force in one direction, the ball would move. The fact that it's stationary means all 3 of these vector forces are canceling one another out. And you would be able to figure out not only the magnitude of that, but the direction that it needs to be in.
Right.
Because, yeah, it can't be purely to the south, right?
Right.
If it was purely to the south, the 75-pound force would win out and the ball would go to the right. It would move that direction. So this third vector of a third player exerting a force is going to have to be at some angle like that. We don't know what it is, but we could figure out what that theta is and the magnitude of the force that's going to be required to keep the ball stationary. Because obviously if I increase this force, the ball is going to go in this direction. So this is kind of a classic vector problem also. But they're all the same. The solution lies in finding its x and y components and adding all the x components together, all the y components together to come up with a new resultant vector. Okay? Now vectors, possibly you're going to give me a vector problem that I'm not going to know how to do. There's,
no, that's the only vector.
If those are the only ones, because there's this thing called the projection of one vector onto another, which for some reason I understand it, but I draw a mental blank whenever I try to actually do it. In other words, what we just have done is projecting vectors onto the x and y, right? In other words, I took a vector that was like that, and I turned it into a y component and an x component and a y component. And so when they say projecting one vector onto another, they're essentially saying take a vector and instead of projecting it onto the x and y components, project it onto an x and y that's been rotated. Maybe I want to project it onto those two vectors instead of x and y.
Oh.
And then changes all the angles. In other words, that angle is now theta, and that's a different angle. So it requires some mental gymnastics or mathematical gymnastics to do this. But it's very helpful if you have a situation where you have somebody sliding down a hill and person's weight is 100 pounds. Well, that's going to exert a downward vector of 100 pounds, but if the sled is on a hill, you don't have to pull with 100 pounds to keep it from sliding. You only have to pull with about 70 pounds, and it won't go anywhere. And this is solved by projecting this vector onto this vector, or vice versa, I'm not sure. But anyway, vectors can get pretty tough. So what else you got, William?
So this next one, it says, a rock is shot from a sling with an initial speed of 40 feet per second and an angle of 85 degrees to the horizon from a height of 8 feet. Physics. We did this exact same stuff in physics back in November.
Yeah.
And I forgot all of it.
Okay.
It would be fantastic right now.
Well, what we have is two components to that slingshot, or the rock. A vertical and a horizontal one.
Right.
We want to figure out both of them, because what happens is the vertical component is affected by gravity.
Right.
The horizontal component is not. This slingshot is going to go horizontally as long as it's in the air. In other words, its horizontal component is 40 times the cosine of 85 degrees, right?
Right.
What's that number? Give me a number on that. But it shouldn't be very much horizontally.
3.48.
Yeah. It's only going 3.48 feet per second in a horizontal direction because it's almost being fired straight up, right?
Right.
Now let's figure out the vertical component.
Uh, 39.8.
Okay. The height of the rock at any point in time as a function of time is h of x equals the magnitude of the vector times the sine of 85 degrees. I gotta look this one up too, hold on. Ooh, that's Moore's theorem. No, I'm back in vector. Let's see. Yeah, this is the classic baseball player hits a ball, does it clear the fence?
Right.
One of those kind of problems. And these are kind of neat, actually, because you really can tell. You can tell whether it clears the fence or not. I got to remember how to do it. Do you have your equations for the vertical? In other words, I believe the vertical, since we're in feet per second, it's minus 16 t squared plus 40 sine of 85 degrees plus its initial height. That is going to be the height of the rock at any point in time. And this part comes from the force of gravity. This part comes from, oh, there's a t there also. Here, let me rewrite it over here on the left.
The 16, that's half the force of gravity, right?
Right.
Okay, or half the acceleration due to gravity.
Yes. And it's half because
32.2.
right, and this is basically the derivative, or the integral of acceleration. Since acceleration is 32 feet per second, if you take the integral of that, you get 16. And that's how this comes out to be. I'm not sure I'm explaining it right, but the initial velocity of the rock comes next. And we know that it's that in an upward direction times t plus 8. Okay? So let me erase all this over here. And this is where you have to start with these problems, is finding how long the rock's going to be in the air.
Right.
Okay? This equation will tell you that. In other words, you want to solve to where the height is 0. That solves for where the thing lands. Okay, so I've got this. That was 39.8 times t plus 8. There's your quadratic.
Okay.
That will produce two solutions for t. One of them will be negative, throw that out. The other will be the time that it hits the ground. Once I have the time that it hits the ground, now I can know how far it goes horizontally. Can you do this quick? I don't know if you can do that quick or not. You have a quick way of solving a quadratic other than the quadratic formula? Let's not waste time doing that because we only have 5 minutes. Unless do you need to turn the answers in for these?
No, they don't need to be.
So these are just practice for you, preparing for the test. Okay. let's pretend we solved it and we got a 2 of -1 and another t of 3. Well, clearly the -1, you can't have negative times. So the t of 3 is this rock hits the ground after 3 seconds. Well, we know its horizontal velocity is 3.48 feet per second. If it's in the air for 3 seconds, then it's going to go 3 times 3.48. It'll go about 10 feet, 10.3 feet. So now I can model. What else did it ask? Did it ask how high up the thing ever gets, or?
Yeah, the maximum height.
Okay. The maximum height comes at the vertex of that quadratic. So solve for t, for the vertex.
And plug in half. Half of the sine for t.
Not half necessarily, because it's not going to be a perfect parabola because it started at 8 feet. If it would have started on the ground, yeah, you double the time. In other words, it would be 1.5 seconds where it hits its peak. But that's not true here. Because remember, the thing goes up, comes down, and then has to drop another 8 feet. So the fact that it hit the ground at 3 seconds doesn't mean that it hits its peak at 1.5 seconds. You have to find the vertex of that quadratic. Okay? And the vertex x-coordinate, or t-coordinate, excuse me, that should be h of t, not x. Okay? The t-coordinates of the vertex is minus b over 2a. So that's relatively easy to find. Minus 39.8, that's b, over 2a, which is minus 32. So there is the time where it would hit its peak. Then it's going to say, what is that peak? Right?
Right.
Plug that time in to your quadratic, the height function, and it'll tell you what the height is at that time.
Okay.
And that should answer everything you need to know. Did it ask any other questions that we didn't answer?
No, that's it.
Yeah, when it hits the ground, how far does it go horizontally and how far does it go up before coming back and hitting the ground? That's a good one to stop on. That's a pretty good one. Just before I go, a more clever one actually is a baseball player. We won't solve this, but I'll show you just for the heck of it. Hits a ball at a height of 4 feet, hits it at an angle of 30 degrees with a velocity of 120 miles per hour on the ball. That's a standard exit velocity for a well-hit ball. Pretty hard, actually. And the question is that 340 feet away, which is a typical ball field, there is a 6-foot fence. Does the ball clear the fence and make a home run, or does it hit the fence? And this can be solved with that height function and vectors. Breaking this thing up into its horizontal and its vertical, and the function for the vertical is the gravity function. The function for the horizontal is real simple. It's just the x component times however many minutes it's in the air.
Okay.
In other words, I will be able to figure out at 340 feet what the height of the ball is. If the height of the ball after 340 feet is more than 6 feet, it clears the fence. If it's less than 6, if it's 5 foot 11 inches, it doesn't clear the fence. It's a double. But yeah, it always amazes me that with this much math, we can answer that question. So all you need is the speed the ball leaves the bat and the angle that it leaves. Of course, in reality, you have to account for air resistance, stuff like that. In other words, all of these problems presume a vacuum. But there's actually formulas that'll handle that too. When you really get into physics, they give you the formulas that count air resistance.
Right.
And how much it's pushing on that ball or slowing it down, and it's different in Colorado than it is in Florida. So it can get pretty complicated determining whether that ball clears the fence or not and whether there's any wind. All right, William, I will let you go. Good luck on your test. Yeah.
Thank you. Have a good night.
Good night. You too. Bye-bye.